Welcome to this explainer. Today we're totally demystifying supervised machine learning. Now, you've probably heard the buzzwords floating around, but we're going to actually look under the hood to see exactly how these models connect inputs to outputs. And don't worry, we're keeping it completely code-free.
Okay, so let's kick things off with a super simple analogy. Imagine teaching a child how to recognize a cat. You show them examples, right? You point and say, this is a cat, this is not a cat, and eventually the kid just kind of figures it out and learns to recognize them on their own. Well, that is literally exactly how supervised machine learning works. It's like you're the teacher, carefully guiding a student by showing them very clear, explicitly defined examples of what's right and what's wrong.
Here's our roadmap for today. We'll cover the core concept, real-world applications, the two types of learning, the algorithm toolkit, how it actually works step by step, and finally, some challenges and takeaways. Moving right into Section 1, the core concept. What actually is supervised machine learning? So, the absolutely crucial element here is labeled data. Supervised learning is basically a framework where the model learns the relationship between an input and a correct output. Labeled data is the absolute key to this whole shebang. It simply means the machine is given both the question, the input, and the correct answer, the output to learn from.
Let's look at a practical example. Say you feed the model the specific features of a house, like its square footage, the neighborhood, maybe the number of bedrooms, as the input. Then you hand it the actual selling price as the correct output. Do this enough times, and the model eventually learns a mathematical rule. It basically figures out, hey, as the size of the house increases, the price increases. It's constantly connecting the dots, completely based on the labels we give it.
Which brings us to Section 2, real-world applications, or supervised machine learning in action.
You might be wondering, okay, where do I actually interact with this? Well, every single time a junk email magically skips your inbox and goes straight to spam, literally saving us from billions of sketchy phishing attempts every single day, or when a bank uses your income history to approve a credit card, you are interacting directly with models trained on labeled data. It's also the secret sauce behind house price predictions on real estate apps. And it even helps doctors with medical diagnoses by matching thousands of past patient symptoms to specific disease predictions. It's everywhere.
Next up, Section 3, the two types of learning. This is all about numbers versus categories.
So the easiest rule of thumb to separate these tasks is looking at the output. We've got regression on one side and classification on the other. If the output you're looking for is a continuous number, think predicting tomorrow's exact stock price or forecasting the dollar value of a house, that's regression. But if the output is about sorting things into distinct buckets or categories, like labeling an email as spam or not spam, or flagging a transaction as fraudulent or legitimate, well, that's classification. To keep it simple, numbers mean regression, categories mean classification.
All right, Section 4, the algorithm toolkit. Let's look at some popular machine learning models.
Here's your rapid-fire rundown of the 7 essential algorithms you really need to know. First, we have linear regression for continuous numbers. Then there's logistic regression, which, despite the name, actually classifies things using a 0 or 1 probability. Decision trees give us those super interpretable, rule-based paths. Support vector machines draw strict mathematical boundaries between classes. K-nearest neighbors relies on proximity to cluster things together, which is perfect for recommender systems. And finally, naive Bayes, an algorithm that leans heavily on probability and is just fantastic for sorting through massive amounts of text. Now, I want to quickly highlight one standout tool here, and that's the random forest. This is what we call an ensemble method. It's basically a really powerful combination of multiple decision trees working together. By essentially crowdsourcing the prediction from a whole forest of individual trees, it aggressively reduces variance and overfitting. This keeps the model from just stubbornly memorizing the training data and then failing miserably when it faces the real world.
Moving right along to Section 5, how it actually works. Let's trace the machine learning pipeline.
Building one of these models follows a pretty strict 5-step assembly line. First, you collect your data. Second, you painstakingly label that data so the machine actually knows what the right answers are. Third, you train your model. This is where the heavy mathematical lifting happens. Fourth, you test the model to make sure it actually generalized the concepts, right? You want to be absolutely sure it didn't just memorize the cheat sheet. And finally, step 5, you deploy it out there to predict the output on brand new, unseen data.
But listen, the golden rule of this entire process is super simple. More quality data equals a better model. Period. It's the classic garbage in, garbage out scenario. You have to remember that this entire pipeline relies 100% on the statistical quality of the information you feed it.
Like we said earlier, a teacher is only ever as good as the examples they provide.
And that brings us to Section 6, Challenges and Takeaways. Let's look at some roadblocks and summarize everything we've learned.
Look, teaching a model isn't magic, and it comes with some pretty severe technical roadblocks. For starters, acquiring that highly prized labeled data, it is incredibly expensive and time-consuming, mostly because real humans usually have to sit down and categorize everything by hand. Then you have the massive risk of overfitting the model, where it gets way too complex, or underfitting, where it's just too simple to learn anything useful. You also have to constantly contend with bias in the data. If your training dataset is statistically skewed, well, your model's predictions are just going to systematically repeat and amplify those exact same biases.
So let's do a quick recap. Supervised learning relies on labeled inputs and outputs to essentially teach a machine. It's cleanly divided into regression for predicting continuous numbers and classification for sorting data into discrete categories. This tech drives the financial, medical, and consumer apps we rely on every single day. And it's powered by a robust toolkit of core algorithms, from simple line fitting all the way to complex random forests.
Now that you understand the foundational mechanics of how these models learn from us, you really have to ask yourself, are you ready to master AI and machine learning step by step? These algorithms are already shaping our future, so are you ready to be the one shaping the algorithms? Keep exploring, keep learning, and thanks so much for joining me